This aircraft has no cockpit, no flight controls, and no seat for a pilot. It is one of the first fully AI-piloted aircraft in the world, but it is not here to replace human pilots. It is designed to multiply them. A real pilot in a crewed jet will command 2 or more of these autonomous wingmen, flying as part of a hive mind-like formation that brings 3 times the weapons into the same airspace. But the entire concept depends on a major unsolved problem, one that will determine whether it survives its first real war. And despite that, the United States Air Force is already deciding which version to buy. The United States Air Force currently operates fewer than 1,900 fighter aircraft. That number has been declining for 3 decades. An F-35A costs approximately $80 million per airframe. Training a pilot to fly it in combat takes 6 to 10 years and costs an additional $10 to $12 million in flight hours alone. A single combat loss eliminates not just an aircraft but nearly a decade of institutional investment. Meanwhile, Russia's S-400 missiles tracks 160 targets simultaneously, engages 80, and covers a detection range that puts crewed fighters under missile solution before they reach weapons release distance. China has expanded its fighter fleet at a rate outpacing American procurement for over a decade. The Air Force cannot buy enough F-35s to close that gap. It has not been able to for 15 years. That is the problem the Collaborative Combat Aircraft Program, or CCA, is designed to solve. But 2 earlier attempts to solve it failed, and understanding how they failed explains why the autonomous wingman concept carries the specific risk it does. The first approach was building cheaper crewed fighters, lower-cost airframes to fill out the declining fleet. Every program that pursued that path hit the same wall. The price reductions required to hit the target eliminated the survivability margins needed to operate in contested airspace. A cheaper aircraft that cannot survive the threat environment is an attrition platform, not a solution. The second approach was unmanned aircraft optimized for permissive environments, such as the MQ-9 Reaper or the Global Hawk. Those platforms proved effective where air defenses were limited or absent. Against a modern integrated air defense system, an MQ-9 is trackable, slow, and unable to maneuver away from a missile. The data link that makes it useful is the same signal a modern radar locates and a modern missile homes toward. Both approaches produced aircraft that were either too expensive to lose or too fragile to risk. The conceptual breakthrough was not a new airframe. It was a redesign of the relationship between the pilot and the formation. One crewed F-35 or F-22 operates as the command node for 2 or more autonomous wingmen. The human manages the mission. The autonomous aircraft suppress air defenses, extend sensor coverage, carry additional weapons loadout, or draw radar emissions to expose surface-to-air positions. One pilot entering contested airspace now enters with a formation. One crewed aircraft plus 2 autonomous wingmen carries roughly 3 times the weapons capacity of a single F-35 operating alone. And if an autonomous aircraft is destroyed, the exchange rate is different. At a target unit cost below $25 to $30 million, the Air Force loses 3 CCA airframes for the price of 1 F-35 and still completes the mission. Anduril's Fury solves this with software called Lattice. Rather than following a pre-programmed route, the Fury is constantly thinking. It reads radar returns, receives updates from the crewed pilot, processes its own sensors, and reevaluates what it should do next, all in real time. If a threat appears that wasn't there at takeoff, the Fury doesn't freeze. It doesn't wait for instructions. It finds a way around it and keeps going. That sounds like exactly what you'd want. And for a while, it was. But here is where the program ran into a wall it didn't see coming. The same intelligence that makes the Fury adaptable also makes it predictable, just not in an obvious way. Every time the Fury encounters a threat and reroutes, it is following a set of rules, and rules repeated across enough engagements form a pattern. Adversary electronic warfare teams figured this out during testing against earlier autonomous systems. They didn't even try to shoot the aircraft down. They jammed the data link and then simply watched. The autonomous aircraft, cut off from its operator, defaulted to a holding pattern, circling at a fixed altitude, on a fixed radius, at predictable intervals while it tried to re-establish contact. After a handful of observations, the pattern was mapped. The aircraft wasn't destroyed, it was just readable. And a readable aircraft in a war is a dead one. The General Atomics Gambit approaches the same problem from a different angle. Where the Fury is purpose-built for a fixed mission, the Gambit is modular. The same airframe can be reconfigured for air-to-air combat, electronic warfare, or surveillance depending on what the mission needs. That flexibility has real value, but it also means extra internal structure, heavier components, a more complex assembly, and all of that pushes the unit cost up at exactly the moment the program needs it to come down, Whether the Gambit can actually hit the $25 to $30 million target with a full combat load has not been publicly confirmed. That number may determine which aircraft the Air Force chooses. But here is what matters. Both aircraft share the same unsolved problem. When the radio link to the crewed pilot is cut, jammed, degraded, severed by enemy action, both the Fury and the Gambit fall back on a recovery behavior. They turn for home. They fly a preset route at a preset altitude, trying to re-establish contact along the way. It is a sensible design and also, in the wrong hands, a trap. An adversary who knows what that recovery behavior looks like doesn't need to track the aircraft actively. They just need to have seen it once, in an earlier engagement, in signals intelligence, or in a test result that leaked. Then they position a missile battery along the expected return path and wait. The aircraft will simply fly straight to them. The solution the engineers landed on is to make the recovery behavior deliberately unpredictable. Random altitude changes, varied timing, small heading deviations that make the aircraft harder to anticipate. And it worked. But it created another big problem. Every degree of unpredictability added for the enemy is also a degree of unpredictability added for the pilot. The human commanding this formation needs to know where his wingmen are going if he loses contact. Make the aircraft too erratic and the pilot loses confidence in the system. Make it too consistent and the enemy maps it quickly. No public test has shown that this balance has been found. The Air Force knows the results of the classified tests, but they have not released them. The first collaborative combat aircraft are expected to enter service before the end of this decade, with a stated goal of more than 1,000 aircraft flying alongside crewed fighters. However, the program has indeed achieved real success in some areas. The unit cost target is achievable at current design points, the stealth geometry is validated, and the Lattice and modular autonomy architectures have demonstrated live decision loop performance in contested airspace test profiles. Also, the force multiplication math holds. One pilot managing a formation of 3 covers the weapon's capacity and sensor coverage that previously required 3 crewed aircraft and 3 pilots. The aircraft that enters contested airspace in the next peer conflict will include airframes with no one inside, executing within rules loaded on the ground before takeoff, in an electromagnetic environment that may have been specifically prepared to make those rules stop working at the moment they are most needed. The balance between unpredictability and control has no clean solution yet. Not in software, not in doctrine, and not in the classified test data the Air Force has chosen not to release. But the hardest problems in military engineering are never the ones that look unsolved. They are the ones that look finished. The CCA program has validated its cost targets, its stealth geometry, its decision loop architecture. On paper, the formation works. But that gap between design behavior and the actual behavior, under real pressure, is where programs get exposed. And it has happened before. The F-117 Nighthawk was considered the most survivable aircraft in the world, tested in total secrecy, invisible to every radar system its engineers could model, and undefeated through hundreds of combat missions. Then one detail its designers hadn't fully accounted for surfaced over Yugoslavia, and a single missile found it. To understand how a system that appeared completely solved carried a hidden flaw, click the video on the screen.